Okay, good morning, everyone. I'd like to thank the moderators for their work. Thank you very much for your introduction. My name is Ahmed Ghadban, and today I'm going to be discussing our study on developing biaxial interaction diagrams for elliptical concrete column sections reinforced with GFRP bars. I have a bit of a sore throat, so I hope everybody can hear me here, so that's good. So the main objectives here is to formulate the solution for biaxial interaction diagrams of elliptical sections reinforced with the GFRP, and then test this solution after implementing it into a software design tool. So as an introduction here, so I start with the introduction of the new ACI for 40.11-22 for concrete structures reinforced with GFRP bars. That opened the door for several challenges that need to be overcome in order to facilitate the application of this code into practice. One such challenge is the need for advanced design tools. When we scanned through the literature and the marketplace, the only softwares that we were able to find are obviously the ones that are for conventional concrete reinforced with steel rebars. But then using these softwares to apply this code is a challenge because of several reasons. One of them is the fact that GFRP behaves differently compared to steel rebars. And then for our particular study, the fact that we have an atypical section, which is an elliptical section, which can be a little bit complicated compared to standard sections like rectangular sections and circular sections. Now, the current softwares for conventional concrete can be applied for any type, some of them at least, can be applied for any type of cross sections, even irregular sections, but the solution is kind of generic. So we believe if we tackle the elliptical specifically, we find a specific solution for this cross section, it would be far more efficient and less time consuming when it comes to the execution time. Another challenge is the biaxial, the fact that we are introducing biaxial moment. Now, this is also available in current softwares for conventional concrete, but the reason I'm mentioning it here as a challenge is because for elliptical sections, it can be like moving from uniaxial to biaxial complicates the problem several folds in comparison with standard sections, like rectangular sections and circular sections. Plus, there's a lack of literature about specifically elliptical sections, how to tackle the problem from a formulation point of view. Now, one could say that all of these challenges basically could be overcome using finite element softwares, for example, because they can employ any kind of materials, any kind of cross sections. But then the question would be, how much time do you need to build these models, and calibrate these models, and then basically execute these models? It's not usually very fast when it comes to finite element models, and that's why we think there is a need to formulate efficient solutions that are specific to every area within concrete structures reinforced with GFRP bars, like columns, beams, walls, like every area, and then within each area you can even have the more specific solutions for each cross sections, each parameters. That would make your solution far more efficient, and when it comes to employing it into a software, it makes it really fast to execute and give you the results, basically. Now, due to the lack of time, I won't be able to go through the entire formulation. I don't want to. When I first prepared the presentation, it took me like 1 hour to rehearse, so I was like, I don't want to be having you fall into sleep, like following all the formulations and equations. So I'm just mentioning one aspect of the formulation, which was a bit of a challenge to us, and then an idea that we came up with that made our solution far more efficient. So as you can see, it's basically the discretization of the concrete sections. So because we have biaxial moment, the neutral axis is not necessarily parallel to the x-axis or the y-axis. It can be inclined. And so we need to discretize the element into 2D elements like rectangular or square elements in order to capture the strain profile of the entire cross section, and therefore give an accurate solution for the interaction diagram. Now, the problem with discretizing it this way creates some irregular elements around the edges, So you can have sometimes triangular, sometimes trapezoidal elements, sometimes even other shapes. And that would complicate the algorithm a little bit and make it tedious to work out. And then also the execution time will not be very efficient. Now, a solution for that, we can actually shift the grids a little bit and make an irregular mesh where we would have only rectangular elements and triangular, and we get rid of all the other elements. And this way, it does simplify the problem for us, but then we still have the issue of execution time. We need sufficiently large elements in order to get something, an accurate solution, and it was taking it a bit of time to execute when we employed it into the software. So we came up with the idea of actually discretizing the cross-section into layers that are parallel to the neutral axis. And this way we don't have to further discretize it into rectangles, because across the entire layer you have a fixed distance from the neutral axis, which means you have a fixed strain, and then you can work out from there by finding the stress and finding the point in the interaction diagram. So this way we only need to find the effective height, and that would be the distance between the two tangents to the ellipse that are parallel to the neutral axis. And then using this height, by dividing it by the number of desired elements or layers, we can get the thickness of each layer, and then we can work our way from there. And we did try both of them in our software, and with this method, we are easily like 10 times faster when compared to this discretization method. And that's not surprising, because if you look at the number of elements we needed, so with this discretization method, the number of layers we needed is about 100 layers in order to get sufficiently accurate solution. Whereas here we needed almost 10,000 elements to get as an accurate of a solution. And that's why the execution time is very different, and it's way more efficient using this. So this is basically one of the challenges we faced when we were formulating our solution. Now, after we were done with our formulation, we implemented the solution into a desktop application using C# language. The full application is actually capable of doing more than just elliptical. We can do a rectangular and circular section, like more the standard sections, include the effective phi, and then we can also do some slenderness analysis in accordance with the ACI moment magnifier method. But this study is just focusing on the elliptical sections because of their complex nature, and the fact that there's a lack of literature when it comes to how to tackle them. Now, we wanted to test our solution against some experimental data, but unfortunately we couldn't find any in the literature. They are not as widely interesting for researchers to experiment on as much as the more standard sections. So we decided to compare elliptical interaction diagrams to rectangular ones that have the same aspect ratio, the same cross-sectional area, the same GFRP ratio, the same number of GFRP bars. So everything is the same except the shape. So one of them is elliptical, and the other one is the rectangular. So we were hoping to see some kind of similarity that would give us some like confidence that our solution is actually accurate and is indeed giving us the right results that we should be getting. So if you look at the interaction diagrams, so we plotted it for different alpha values, so alpha being the angle of the axis about which the resultant moment is acting. So we ran it from 0 to 90, so this is bending about the strong axis, and 90 would be bending about the weak axis. So the black lines, I don't know if the color is very visible, but the black lines like this one, these lines are for elliptical, whereas these are for, they're not very visible for the others, but they are supposed to be gray for the rectangular sections and black for the elliptical sections. And as you can see, there are a bit of similarity between them, especially if you look at the area where you have high compressive force. So they are quite similar. but then you start getting some like difference, like visible difference when you are in this region, when you have low compressive force or high tensile force. So you see a bit of difference in the moment capacity. For example, if you look at these two curves, so the moment capacity for the rectangular at the same load is actually bigger than that for elliptical. And that's not surprising. If we superimpose both sections on top of one another, you see that the main difference between them would be the layout of the GFRP bars. So you see the GFRP bars, we have two in the middle for elliptical, we have nothing in the middle for rectangular. And then on the edge, we have only one for the elliptical section. We have two of the rectangular section. So, and that makes sense that we have this difference in this region where the GFRP bars action is more prominent. You have a big difference because the layout of the GFRP bars in the tension zone is very different between the two sections. And that's why you have this difference. But overall, looking at the entire curve, I think they have some good similarity that would give us some confidence in our solution. But we are still hoping to be able to test them in the future against some experimental data to verify our results even more. Now, we went ahead and tested some of the ACI recommendations and comments. One of them is this comment, ACI for 4111-22, R10.7.3.1, which deals with the circular cross sections. And what this comment says basically is if you have a circular section with less than 8 rebars, then you can no longer assume the axis symmetry, basically. You need to be careful how do you arrange your rebars or how your rebars are arranged because that will affect your interaction diagram. So in this case, you cannot deal with circular section as uniaxial bending. You have to deal with them as biaxial bending because depending about which axis you're bending, you can have a significantly different, that's what basically the ACI comment is saying. You can have a significantly different interaction diagram. So since we have the solution for elliptical, we can simply make a solution for an elliptical section with a 1-to-1 ratio, make it a circular section, and then we can test, we can find the interaction diagram for several alpha values for biaxial bending, basically, and then we can figure out whether this comment, ACI comment, is really significant when you have less than 4 rebars or not. Now, the reason we would have such a significant difference in the interaction diagram depending about which axis you're bending is because if we have only 4 rebars, for instance, the gap between them is quite large. And so if you're bending about this axis versus if you're bending about this axis, the arrangement of the rebars in the tension zone is very different. So about this axis, you have the tension zone, you have only 1 rebar at the far end. You probably have the contribution of these if this axis is shifted up a little bit. But then if you bend about this axis, for example, 45 degrees, then the tension zone, the layout of the rebars is very different. Whereas if you make them 8 rebars, the gap between them is no longer large. And so it does not become as significant if you bend about this axis. You have this arrangement of rebars. If you bend about this axis, you have this arrangement of rebars in the tension zone. So it becomes more similar. The arrangement of the rebars become more similar. And that's why the ACI code is saying after 8 rebars, you don't have to worry about biaxial bending. You can just deal with it as a uniaxial bending because it's not going to be very significant, the difference. So we found the interaction diagrams for a circular section with 4 rebars for alpha values from 0 to 45, because beyond that it's just going to be symmetrical. It's going to be mirroring the others. So the maximum difference between alpha equals 0 and alpha equal 45. As you can see, these are the interaction diagrams. Very similar when we are in the high compressive force region. Then you start to see some noticeable difference in the tension when you have tensile force, and that's basically because in this region you have the contribution of the GFRP bars would be more prominent, and the layout with the rebars would play a role over here more than it does over here. And that's why we have a noticeable difference in this region, as you can see. Now we went ahead and tested the other like 4 rebars, 5, 6, 7, 8 rebars as well. And this time we only plotted 2 interaction diagrams, and basically these 2 would be the ones that have the maximum difference between them. And as you can see, if you have 8 rebars, it's almost the same. There's not much difference about which axis you bend. But I would say even 7 rebars and even 6 rebars, you don't have much difference. So, so based on these data, we can fairly say that if we relax the ACI comment to 6 rebars instead of 8 rebars, we can still deal with our section as a uniaxial bending problem instead of having to go through the biaxial bending. Now, 5 rebars and 4 rebars, you start to see some noticeable difference between them. Now, whether this is a significant difference or not, probably is more of a question for those who have more practical experience than myself. So, so if this difference is not really that significant in practice, then the ACI comment can basically be ignored, because obviously you cannot have less than 4 rebars in a circular section. Now we also tested the other recommendation for ACI, which is to neglect GFRP in compression. So our solution was following the ACI 440.11-22, and that basically recommends to neglect the GFRP action in the compression zone. So we wanted to see what we would have what's the difference if we include the action of GFRP. So and then we plotted them here. You see the solid curve is for the one that complies with the recommendation of ACI, and then if we have the full value of the modulus of elasticity of the GFRP, you get the maximum interaction diagram, some increase in the moment capacity. And then if we put it only with a value that's half the modulus of elasticity of, so basically in compression we put half the modulus of elasticity of GFRP, that's in tension, you will get the curve in the middle. And having a look at it, we could say that this ACI recommendation is actually reasonably conservative, especially if you're only considering half of the modulus of elasticity in compression. So the ACI recommendation is reasonably conservative. So to conclude, basically we were able to find the solution for the biaxial interaction diagram for elliptical columns with reinforced with GFRP bars, and then one of the main things that resulted in an efficient solution for us, which was very time efficient when it comes to execution time, is the introduction of these concrete layers, which made our program like almost 10 times faster compared to the more of the standard discretization method using rectangular mesh. We compared our results from the elliptical cross-section to rectangular cross-sections, and we verified our results are reasonable. We would like in the future to further test it against some experimental data if they come out in order to have like more confidence in our solution. We tested the ACI comment for circular sections, and we can safely conclude that this comment is at least relaxable to 6 rebars, if not ignorable. As I said, if we consider that difference in 4 rebars not that significant. And we tested the recommendation to neglect GFRP in compression, and we think, based on our results, that it's reasonably conservative to follow these ACI recommendation. And with this, I conclude my presentation.